This is a video from the Exam 2 review in my linear algebra class, and this is from part 2. Let's take a look at problem 7. Determine whether the set containing 1 minus x, x squared, 2x plus x cubed, and 2 plus x cubed spans P3. So what I'm going to do is I'm going to let a plus bx plus cx squared plus dx cubed belong to P3. And remember, P3 is the set of all polynomials less than or equal to degree 3. So from here, I'm going to set C1 times 1 minus x plus C2x squared plus C3 times 2x plus x cubed plus C4 times 2 plus x cubed, and I'm going to set this equal to a plus bx plus cx squared plus dx cubed. Okay, from here we can say c1 minus c1x plus c2x squared plus, and then if I distribute, right, I get 2c3x plus c3x cubed plus 2c4 plus c4x cubed. That whole entire thing is going to equal a plus bx plus cx squared plus dx cubed. Now you want to attack this very, very systematically. So I'm going to collect the terms that are constant, the x terms, the x squared terms, if there are any, and the x cubed terms. So notice how I see a C1 and a 2C4. Okay? So what I'm going to do is I'm going to write C1 plus 2C4 right here. Now, I'm going to go minus C1x right here plus 2C3x minus C1x plus 2C3x. And then I look around, and then I see a C2x squared plus C2x squared right here. Then I'm going to go plus C3x cubed plus C4x cubed. And then notice how I have 1, 2, 3, 4, 5, 6, 7 terms. 1, 2, 3, 4, 5, 6, 7 terms. So I got all the terms. And remember, this is equal to a plus bx plus cx squared plus dx cubed. Now, so this says C1 plus 2C4 plus negative C1 plus 2C3x plus C2x squared plus C3 plus C4 x cubed, right? This is equal to a plus bx plus cx squared plus dx cubed. Very systematic, okay? Now, what does that mean? Well, if I take C1 plus 2C4, I get A back. Negative C1 plus 2C3 equals B. Okay? C2 equals C. So we're done there. And then C3 plus C4 equals D. Okay? Now, if we look at these first two equations and add them, can we agree that I get 2c3 plus 2c4 equals a plus b? And then I get c3 plus c4, looking at the fourth equation, equals d, right? Now, if I multiply through by 2, are we in agreement that a plus b equals 2d? Now, this is a problem, okay? Because not all polynomials will have this condition that a plus b equals 2d. So all I have to do is construct a polynomial where that doesn't work, right? Does that make sense? So, in other words, if I take 1 plus 2x plus 3x squared, now plus, now we have to be careful, right? A plus b equals 2d. So when I construct my polynomial, I'm just going to make sure a plus b does not equal 2d, where d is the coefficient of x cubed. So now, notice that 1 plus 2 is 3. So all I have to do is put 7x cubed. This belongs to P3. But 1 plus 2x plus 3x squared plus 7x cubed cannot be written as a linear combination of these polynomials. So we have 1 minus x, x squared, 2x plus x cubed, and 2 plus x cubed. And so therefore, 1 minus x, x squared, 2x plus x cubed, and 2 plus x cubed does not span P3. And that's how you do problem number 7. Let's take a look at problem 8. Now, prove. We're going to prove B, which is the set of vectors 2, 0, 4, 1, 1, 0, and 1, negative 1, 0 is a basis for R3. Now, I want to show you how this dimension theorem is going to work. We're going to learn about this. Now, set A times 2, 0, 4 plus B times 1, 1, 0 plus C times 1, negative 1, 0. We're going to set that equal to the 0 vector. Now, from here, we can say 2a plus b plus c equals 0. And then we can go b minus c equals 0, right? And then from here, I can say 4a looks like equals 0, which implies A is 0, right? Once A is 0, then we know B plus C equals 0, right? Because I'm going to replace A up here with 0. And B minus C is 0. And so therefore, B equals C equals 0. What does that mean? B is linearly independent set with 3 vectors. Now, here's the thing. This is really important. We want to show B is a linearly independent set with 3 vectors. Also, this must be stated. The dimension of R3 is 3 because we have the standard basis, right? The standard basis for R3 has 3 vectors in it, which tells me that the dimension of R3 is 3. And so by a theorem, right? By theorem, we can conclude B is a basis for R3. That is completely legitimate. The dimension of R3 is 3, and we showed that one of the conditions hold, therefore both conditions have to hold. Now, here's what we're going to do next. What I'm going to do is I'm going to set the vector 1, -4, 5 as a linear combination of the vectors in set B. So in other words, I'm going to take the vector 1, -4, 5 and set it equal to 2, 0, 4 times A, right? Plus B times 1, 1, 0 plus C times 1, -1, 0. Okay, so from here, we can say 2A plus B plus C equals 1, right? And then we can say B minus C equals -4. And then we can say 4A equals 1, which tells me A equals 1/4, right? Do you agree? A is 1/4. And so if I take 2 times 1/4, I get 1/2. And so therefore B plus C equals 1/2. B minus C equals -4. So 2B equals, what is that? -7/2. So B is -7/4, right? And what that tells me is that C has to equal 4, I believe, right? But we can double check that. Actually, let's double check that. So B is -7/4. So I'm going to plug that back in. -7/4 plus C equals 2/4. Haha. It's good I checked because 1/2 and 2/4 are the same. So C is equal to 9/4. So I solve for A, I solve for B, and I solve for C, right? And so the coordinate vector of V, and by the way, now note, V is the vector 1, -4, 5. And so the coordinate vector of V relative to B is, and then the first coordinate is 1/4. The second coordinate is -7/4. And then the third coordinate is 9/4. So that's how we do, this is problem number 8, all of it. And that's a good stopping point for this video. And so this is a video from the Exam 2 review, and we looked at problems 7 and 8. Okay, thank you.